Okay, let's talk now about solving rational inequalities. There's two types of questions that you might be handed. One is on a graph and the other is algebraically. Graphically, it's pretty easy. You quite simply just look at the graph and you're just going to highlight the parts that satisfy the inequality. So for example here, I'm being asked to find when this function, so x plus 3 over x minus 2, as shown in the graph, is greater than or equal to 0. This is asking when it is going to be above or on the x-axis. Remember, greater than means above or touching. And so where is that happening? Well, our top right corner, I think we can pretty clearly see, is going to go on forever above that horizontal asymptote. And it looks to me like there's probably a horizontal asymptote around 1. So that's going to be always positive. This section here would be going on to infinity, but where does it start? Good question. Looks like there might be a vertical asymptote as well at 2. And so the section in the top right-hand corner of our graph is anything from 2 to positive infinity. Remember, we don't include a square bracket on 2 here because it's never actually going to touch 2 because 2 is that vertical asymptote. Now, what about on the bottom left corner of our graph? It looks like there is our x-intercept at 3. That is going to be counted because we also want to know when the function is equal to 0. And then we're going to go every way up to the left as it approaches the horizontal asymptote that way. This section here starts from negative infinity and it goes all the way to negative 3, including negative 3, which is why we use the square bracket there. Okay, so we can conclude, we can say therefore the interval that satisfies the given inequality is, and I'm going to write negative infinity to negative 3 inclusive, union 2 to positive infinity. Okay, pretty straightforward. Algebraically, we're basically going to be combining the techniques that we saw in lesson 6.1 about solving rational functions with our sign chart that we saw with our polynomial functions way back in unit 2. Okay, so a couple of steps here that we're going to go over. First things first, if it's not already the case, you want to move everything over to one side and simplify. In lesson 6.1, if you were somebody who cross-multiplied over the equal sign, that's okay, but you can never, ever, ever, ever cross-multiply over an inequality. You have to go the slow way by moving things to the left, finding a common denominator, and then simplifying, okay? You cannot cross-multiply over an inequality. Then in order to set up our sign chart, we are going to be figuring out what are the restrictions on the denominator, and then when is our numerator equal to 0. And these two things are going to help us find our different sections on the number line in order to then set up an interval table. And then just like for polynomial inequalities, we set up a table, we pick a number at each interval, we check it, and then we write our conclusion. So let's look at our first question here. Find the interval that satisfies the inequality x minus 5 over x plus 2 is greater than 0. We do not include 0 because it is not also equal to. Okay, first things first, where's our vertical asymptote? Our vertical asymptote is located when the denominator is equal to 0, and so x is negative 2. Our x-intercept is when the numerator is equal to 0, or x is equal to 5. So we plot these numbers on a number line to help us find our intervals. I didn't have enough room. There we go. Okay, so we've got sort of three sections here. We have -2 and to the left is one section. We're going to have everything between -2 and +5 as the other section. And then we'll have from 5 onwards as our third section. So we can set up our table here. So we have everything from -infinity to -2. We'll have a column just for -2. We'll have a column between -2 and 5, a column at 5, and then a column from 5 to +infinity. And then we're just going to have two rows here. We're just going to have our entire function, so x minus 5 over x plus 2. That's what we're going to be doing here. And then we'll have our sort of concluding row. Now, before I even go to fill this in, I'm going to ask myself which columns or column represents my vertical asymptote. We never touch the vertical asymptote. We get close to, but we never touch it. And so our function will never be on there. We're not going to check it. Our vertical asymptote is that x is equal to -2. So I'm literally just going to scratch out that column because it is our vertical asymptote. There is no point in checking it. Okay? On our first interval here, between -infinity and -2, I'm going to check the value -3. And I'm going to check into my function here. -3 minus 5 is -8, so I'm going to write a little negative there. And then my denominator will be -3 plus 2, which is also a negative. A negative divided by a negative is a positive. Okay, second interval, I'm going to test at 0. 0 is a nice easy number. 0 minus 5 is a negative. 0 plus 2 is a positive. Negative divided by positive is a negative. At x is equal to 5, my numerator becomes 0 because I've got 5 minus 5 is 0. And my denominator is positive. Overall, this is 0. And then last but not least, I'm going to test the number 6 in my third interval there. 6 minus 5 will be a positive number. 6 plus 2 will also be a positive number. And so overall, my function is positive here. We were asked to determine where the function is greater than 0 and to not include 0. So that is on these two ranges here. Between -infinity, -2. And between 5 and +infinity. So I can write a therefore statement. I can say therefore x minus 5 over x plus 2 is greater than 0 on the intervals -infinity to -2 union 5 to infinity. Okay, let's do question 3 now. This will be our last one to really highlight the fact that you cannot cross multiply. You may be very comfortable with cross multiplication, but you cannot cross multiply over an inequality. We're going to rearrange and move everything from the right-hand side over to the left-hand side. And I'm looking to combine these, so I need to create a common denominator here. My common denominator will just be multiplying the two denominators together. So my left fraction will become, I have to multiply the top and the bottom by x plus 3. My right fraction, I need to multiply the top and the bottom by x minus 1. So now I have a common denominator I can combine, but first things first, I'm going to expand my numerators. My first numerator I'll FOIL out. It'll be x squared plus 2x plus 3x plus 6. My second numerator will be x squared plus 4x minus x minus 4. And I'll combine. I see I've got x squareds that will end up canceling out. I'll check here. I have a positive 2x plus 3x, so that's 5x. Take away 4x is 1x. Take away negative x is 2x. Then I have a 6, take away negative 4, 6 plus 4 is 10. And all of that again greater than or equal to 0. And then I'm just going to finish off by factoring my numerator here. I can common factor out a 2. Alrighty. Okay, this is the simplest form of my question now, and it's pretty easy to see what everything is, or sorry, where everything is. Let's first find our vertical asymptotes. And that's by setting both terms in the denominator equal to 0. So I have a vertical asymptote at x is equal to 1. And I have another one at x is equal to negative 3. My x-intercept is located when I have my numerator equal to 0, or in this case, x is negative 5. Awesome. Now we set up that number line again. Oh, that's a nice diagonal number line. Try that again. Better. Okay, and I have to go from negative 5, I have a 0, and I have a negative 3. Oh, I skipped a whole bunch of numbers there. Okay, so I've got 3 intervals that I'm working with because I have an x-intercept at negative 5, and then I have a negative 3, and I have a 0. So my first sort of interval is here, is everything between negative infinity and negative 5. The second interval will be between my x-intercept of negative 5 and my vertical asymptote of negative 3. My third interval will be everything between negative 3 and 0, so between those two vertical asymptotes. And then last but not least, my fourth one will be everything after my second vertical asymptote there. Okay, lots of different intervals to check. I'm going to add some columns here. So I need between negative infinity and negative 5. I need at negative 5. I need everything between negative 5 and negative 3. I need at negative 3. Ooh. I need everything between negative 3 and 0. I need at 0. And then I need everything from 0 to positive infinity. And I write my function down here, 2x plus 5 over x minus 1, x plus 3. And then I say to myself, okay, which of these columns represent vertical asymptotes? X is equal to 1. Oh, I messed up there. Our 0 section should be 1. No problem. All the way to here. So, second section will be between negative 3 and positive 1, and then the fourth section will be from 1 onwards. Okay, and so I just have to fix my intervals here. I have at 1, I go from -3 to 1, and then from 1 to positive infinity. There we go. Okay, anyway, so I check where my vertical asymptotes are. I have a vertical asymptote at x is equal to 1, so I throw out this column because we will never touch there. I also have a vertical asymptote at -3, so I throw out this column because we're never going to touch that one. And now it is time to test. Okay. So I'm going to test my first function here, my first interval, I should say, at -6. Let's try that at -6. 2 will always be positive. -6 plus 5 is negative. -6 minus 1 is negative. -6 plus 3 is negative. I have 3 negatives here, so overall my function is negative. At x minus 5, that's our x-intercept, so we already know the whole function is going to be equal to 0. On the interval -5 to -3, I'm going to test -4. 2 will always be positive. -4 plus 5 is positive. -4 minus 1 is negative. -4 plus 3 is negative. Ooh. 2 negatives, 2 positives. Overall, my function is positive. Okay, on the interval between -3 and 1, I'm going to test 0 because it's nice and easy. 2 is always positive. 0 plus 5 is positive. 0 minus 1 is negative. 0 plus 3 is positive. Overall, my function is negative. And my last interval here, I'm going to be checking between 1 and positive infinity. I'll use the number 2. 2 is always positive. 2 plus 5 is positive. 2 minus 1 is positive. And 2 plus 3 is positive. The whole thing is positive. So our original question was asking us, when is it greater than or equal to 0? When is it positive or at 0? Well, it's positive here, and it is 0 at -5. And so I can write my therefore statement at the very end. I can say therefore 2x plus 5 divided by x minus 1 times x plus 3 is greater than or equal to 0 on the intervals. I have -5 and then also between -5 and -3. So I'm going to write my interval -5, -3. I'm going to use a square bracket for -5 because I do need to include the fact that it's equal to 0. -3 though, that's one of our vertical asymptotes, so I'm going to include a soft bracket at the end there. And then I'll write my union. And then my second interval is between 1 and positive infinity. Infinity always has a soft bracket, and then 1 again is our vertical asymptote, so we have to use a soft bracket there. Okay? So to recap, we rearranged our equation if we needed to. We found our vertical asymptotes. We set up, and our x-intercept. We set up a number line to identify the intervals we needed to test against. And then we followed what we knew from polynomial equations in terms of picking a number, testing them against the equation, and then determining the results according to what the original question was asking, and then concluded with a therefore statement. Okay? Great work, everybody!